All right, so electrodes and potentiometry. So potentiometry is the use of electrodes to measure voltages that would provide chemical information. Electrodes use respond selectivity to specific analytes in solution or in the gas phase. Ion selective electrodes are about the size of a pen. Actually, like that would be a normal thing to purchase, but you can purchase ones that are vastly smaller, far, far, far tinier. They make ones the size of chips. You know, like a little chip. It's like less than half centimeter in diameter. Yeah. So they can go very, very tiny. I think there's actually one that they recently made that's on the micro scale. So they can get very impressively small. Anyways, it's a field that's improving rapidly. Ion selective electrode, and indicator electrode, also called a working electrode, is going to respond to an analyte activity. And notice the indicator or working electrode is the one that's going to respond to a specific analyte. Okay? The name actually gives you a huge hint, right? It indicates that you have that analyte. Indicator electrode, right? The reference electrode is going to maintain a fixed reference potential. There's a few different reference electrodes that people like to use. The SHE is like a really nice one if you could, right? But notice it has H+ and it has a freaking gas. So that's not exactly a recipe for a stable electrode, is it? No, that's not something you can leave out on the counter for a year and you're going to be okay when you use it the next time, is it? So, and these things can be digitally calibrated to automatically adjust and give you as if that other electrode's 0, right? Because if you put an electrode in there that's standard, then it's going to give you a certain voltage. And so you can just, adjust, literally subtract off that voltage, right? Every time. So what are typically used are silver chloride and calomel reference electrodes. These are very convenient to use. They store well. They don't react with a lot of things. They don't take on water. They don't need water to keep them solvated. They're just incredibly easy to use. They're very, very reliable, whereas an SHE is not. So the two half-cell reactions are going to be written as reductions, of course. The right electrode here is an iron one. And so this one is going to be selective for iron, right? We're looking at the concentration of iron. The left electrode here, that's our standard. And so that's going to be the silver chloride electrode in this case. So it's a silver chloride electrode. And it uses this redox reaction of silver chloride going to silver. Notice both of these are solids. And so they don't end up, escaping in the atmosphere or having issues if you run out of water in the electrode. You just need to put more solution in later. No problem. So it's very reliable. This has an E0 here of 0.222. And so you can just correct it to 0 every time, right? You know what that is. You can put it in the chip that is 0.222 instead of 0. So the electrode potentials are going to be, well, you have your right electrode that's 0.771 versus the 0.222, right? And so you take the E+, which has an E0 of 0.771. This is a 1 electron reaction, so it's over 1. And this is just the Nernst equation, right? The E- is only going to have one term in terms of concentration, which is the chloride, because all the other ones are solids, meaning they go into unity. Does anybody have any questions about that so far? No? Okay. So your cell potential is going to, again, be the E+ minus the E-. Okay? The chloride is going to be fixed by the solubility of the KCl, which if you look closely, you use a saturated solution of that. If you have a saturated solution, the chloride concentration will always maintain a constant concentration. Okay. By the way, again, notice that the KCl is going to be largely in the form of a solid again, and whatever water you have will become saturated in your probe by that KCl. That's cool, isn't it? Don't you like that? Also, note that the chloride, again, is being maintained at a constant chloride. All right, so the only term that actually changes is this iron 2 plus, iron 3 plus concentration ratio. So when you use this, the changing of the iron 2 plus versus iron 3 plus concentrations will give you whatever electrical signal you get. Okay? That's going to be the only term that changes. So that's going to be the only thing that determines how different your electrical potentials are. These are the standard ones, right there. Notice that this silver versus silver chloride one is not actually at an E naught when you use it, because you have a saturated chloride solution, not unity, right? So you always end up with an E for the saturated KCl, for the saturated chloride solution, which will give you this value right here. Okay? Note that is a little bit different than E naught, right? All right, this, by the way, is what this looks like inside. So notice you have a wire lead here. You have an air inlet that allows the electrolyte to drain slowly through a porous plug here. You have a silver wire bent into a loop. The loop is so that you can have silver chloride paste suspended on the loop. See that? You have an aqueous solution. This is going to have potassium chloride and silver chloride in it. On the bottom, you're going to have solid KCl plus some AgCl that also ends up getting mixed in because it comes off of here, right? I mean, it's real world, right? Not everything's going to stay where it's supposed to be. On the bottom, you're going to have a porous plug here for contact with your external solution. This is the salt bridge, by the way, the porous plug here. Remember I said that you don't need it to necessarily be a salt? Well, here you go. You got your porous plug. Okay. Everybody's comfortable with the wire lead is the one that goes off to here. You're all okay with that? You understand that okay? This anode here is this stuff right here. That's that reference electrode. See that? And the porous plug allows it to be in contact with this iron 2 plus, iron 3 plus solution. The other side is just going to be your cathode, which can just be a platinum wire. That's just to transfer electricity over here. Yeah, you might get some plating out in some situations, but platinum is very easy to clean because it's very resistant to acids and such. Okay, so this is a calomel electrode. This one's not used as often, as far as I'm aware, anymore because of the presence of mercury. It's actually very hard to get mercury 2 plus now, in case you're curious. So this is the half reaction for a calomel electrode. It's going to have mercury chloride, solid, takes on an electron, and gives you mercury liquid and chloride ion. This would be the E naught for it. Again, it's going to be with saturated KCl to keep that chloride ion constant, right? In a nice saturated solution. Yes, theoretically, you could actually use up the chloride ion, but that's not, you can refresh the chloride ion as well, okay? By running these electrodes backwards. That gives you a slightly different E. This calomel electrode, by the way, is called a saturated calomel electrode, and that's usually abbreviated SCE. This is what it looks like inside. It looks pretty similar to the other one. Just note that it is going to have a little test tube inside where the liquid mercury will gather. Okay. All right. Please note that if you ever do use these standard electrodes, and actually physically use them, be careful with these things, okay? They're mostly composed of glass. Most of them won't work if you shake them up because they don't have anything to contain like the saturated KCl, right? If you shake up a saturated solution, it causes the solid particles to scatter everywhere. So they're not something that you want to shake, okay? They're something you need to leave and then very carefully use. But there are ones that are designed that have more complex designs that can avoid getting messed up by shaking and all sorts of stuff. Anyways. So now that we're using standard electrodes that are not SHEs, do not have a 0 on the scale, we have to convert these, don't we? So we have to use these with a difference reference scales. So right here we see a difference reference scale, a different reference scale. Notice that the SHE is 0 here, right there. Versus an SHE, everything that you measured against would just be its number, right? Because it would always be -0. But if we're using something else, like an AgCl or an SCE, those are not 0. Those are up at 0.197 and 0.241. So let's say we have something that's 0.22. If you measure it against the SHE, it would just be that number, right? But if you measure it against an AgCl, you would get a number of negative 0.417 volts, right? And that's because you're adding on that number right there, 0.197, right? So what would you need to do to get the voltage as versus a 0 reference, or a voltage for the net cell? Well, you'd have to add that 0.197 to reduce that number, wouldn't you? In magnitude. Okay. Now, I'll be honest, there's a lot of the standard electrodes now come in like package deals. Most of them don't come like this anymore that I've seen. Most of them come in essentially a little package that you'd hold the top of that has a digital representation on top that has 2 electrodes coming out of it that you would just stick in solution. They don't come in this 2-part thing. And most of them now come with a chip that does that work for you automatically. So it would automatically convert for you. But you do need to understand what's going on in case you ever set something up. Or you use an older electrode, or you have a new electrode that's not working, or whatever, right? You don't get to black box anything. You need to understand. So remember that if you use one of these other standards, they're non-zero, right? So you always need to correct that standard to 0. Metal electrodes will develop an electrical potential in response to a redox reaction at the metal surface. Ion selective electrodes are not based on redox processes, but on a selective binding of one type of ion to a membrane. This binding of an ion to a membrane would generate a potential. So remember, if it's just the metal electrode, it's going to develop electric potential to any redox reaction at your metal surface, period. Doesn't matter what metal it is. Ion selective ones will need some sort of selective binding to occur. Platinum is the most common metal indicator electrode. This is because it's relatively inert. It's also relatively easy to clean. Most of the stuff that's going to plate out on it can be cleaned with a strong acid, and platinum's pretty good at resisting that. Gold and various types of carbons are also used as indicator electrodes. Again, they're a good conductor. It's relatively inert. Gold is typically not as inert as platinum, though. Carbon has been one that's a lot of work has been done on like different types of spiked carbons and different structures. And this is getting quite advanced. I'm not actually up to date on the newest stuff. But you can do a lot with carbon indicators. They work best when their surfaces are large and clean. If they're corroded, obviously you will not get a lot of surface contact, right? So you'll get very little signal. Your limit of detection will go down drastically. Oh, what time is it? Okay, we'll pick up on this one next time. You all have a great day. Andy.